All right, we're going to continue our lesson on finding complex zeros of polynomial functions. Okay, so we're going to move on to the next type of example where the directions here ask us to use the given zero to find the remaining zeros of the function. All right, so I'm going to work through this one with you, and then the next example is going to be one for you to try on your own. And for this one, we're given the function f of x, which is equal to 2x to the fourth plus 5x cubed plus 5x squared plus 20x minus 12. And then we are given a complex zero of negative 2i. Okay, so again, we're going to take what we talked about earlier on in the lesson, and we know that if negative 2i is a zero, then its conjugate, positive 2i, is going to be a zero as well. Okay, so once we determine that those two complex conjugates are zeros of the function, what we can do is we can actually construct a polynomial that gives us those two zeros. Okay, and the way that we're going to do that is we're going to take x minus each of those zeros. So x minus the top zero, negative 2i, x minus negative 2i is the same thing as x plus 2i. That's going to be a factor. And then x minus the second zero, 2i, is going to be a factor as well. Okay, and if we were to multiply this out, again, this is of the form a plus b times a minus b. That's going to multiply out to a squared, which is x squared minus 2i quantity squared, which is going to become x squared minus 4i squared. And then again, we know I squared is negative 1. So that's x squared minus 4 times negative 1. That becomes x squared plus 4. Okay, so that is our polynomial that gives us these two zeros. Okay, well, if we know that that polynomial gives us those two complex zeros, then that also tells me I should be able to take this polynomial here and long divide it into my function f of x, and that should give me a remainder of 0. Again, because when we know something is a factor, we know that if we divide that into our polynomial, that's going to give us a remainder of 0. So we're going to take the polynomial x squared plus 4, but instead of writing it like that, I'm going to write it as x squared plus 0x plus 4. And that way all of the terms line up whenever I do long division. Okay, and we're going to long divide that into our polynomial 2x to the fourth plus 5x cubed plus 5x squared plus 20x minus 12. And again, I can't use synthetic division here. I can only use synthetic division whenever I'm dividing x plus or minus some number into a polynomial function. Okay, so to long divide, we want to think to ourselves, what times x squared gives me the first term, 2x to the fourth? And that's 2x squared. So I'm going to distribute 2x squared across all three of the terms out front. So 2x squared times x squared is 2x to the fourth. 2x squared times 0x is 0x cubed. 2x squared times 4 is 8x squared, and then I'm going to subtract that result. All right, so that's going to leave me with 5x cubed. 5x squared minus 8x squared is negative 3x squared. And then we're going to bring down the next term in line, which is 20x. Okay, so again, we want to think to ourselves, what times x squared gives us 5x cubed? And that is positive 5x. So when I distribute 5x across all three terms out front, that gives me 5x cubed plus 0x squared plus 20x, and then I can subtract that result. When I subtract, that gives me negative 3x squared. 20x minus 20x becomes 0x. And then we bring down the next term in line, negative 12. And then what times x squared gives us negative 3x squared? That is negative 3. So when I distribute negative 3 across all three terms, we get negative 3x squared plus 0x minus 12. And then when we subtract, we get the remainder of 0 like we were supposed to get. Okay. All right, so what we want to do is we want to find the zeros of 2x squared plus 5x minus 3. And that is going to be factorable. I'm looking for two numbers that multiply together to give negative 3 times 2, which is negative 6, and add to give 5. And that is going to be 6 and negative 1. So I'm going to break that middle term up into two terms using these numbers here as coefficients. So that's going to be 2x squared plus 6x minus x minus 3. And then factor that by grouping. So I can factor 2x out of the first two terms, leaving me with x plus 3. And I can factor negative 1 out of the next two terms, leaving me with x plus 3. So that factors to 2x minus 1 times x plus 3. Okay, so once I have that in factored form, we have all of our zeros. So the value that makes that factor 0 is x is equal to 1/2. The value that makes that factor 0 is x is equal to negative 3. And then we have our two zeros from earlier in the problem. X is equal to negative 2i, and x is equal to 2i. All right, so those are our 4 zeros of that polynomial function. 2 of them happen to be real numbers, and 2 of them are imaginary. But all 4 of those numbers are complex. Again, because real numbers belong to the set of complex numbers. Okay, so I want you guys to try number 2. Very similar problem. So f of x here is equal to x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. And we're given that that polynomial has a complex 0 of 1 plus 3i. Okay, so go ahead and pause the video while you work on that example. Okay, so let's go ahead and work through this together. So again, we are given a excuse me, a complex 0 of 1 plus 3i. So its conjugate 1 minus 3i has to be a 0 as well. So we want to construct the quadratic function that gives us those two zeros. So we're going to take x minus each of those zeros, and those are going to be factors. Okay, so we're going to distribute, just like we did in class, we're going to distribute negative 1 across both sets of terms. So this becomes x minus 1 minus 3i, and then x minus 1 plus 3i. And then we're going to regroup these just like we did in class. So we're going to group the x minus 1s together. So again, this is of the form a minus b times a plus b. That's going to multiply out to a squared minus b squared, okay, which is x minus 1 squared minus 3i quantity squared. Okay, so if we FOIL out x minus 1 squared, that's going to become x squared minus 2x plus 1 minus 3i quantity squared. So I have to square both 3 and I. So 3 squared is 9 times I squared. I squared is negative 1. So this becomes x squared minus 2x plus 1 plus 9 is going to be plus 10. Okay, so that right there, that quadratic, is the one that gives you 1 plus 3i and 1 minus 3i as zeros. And then we want to long divide that quadratic function into the function that we're given. Okay, so we're going to long divide x squared minus 2x plus 10 into our given polynomial. So that's x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. Okay, so again, we want to think to ourselves, what times x squared gives us x to the fourth? Well, that's x squared. I distribute x squared across all three terms out front. So that's going to become x to the fourth minus 2x cubed plus 10x squared. And then I'm going to subtract that result. So the x to the fourths cancel. Negative 3x cubed minus negative 2x cubed is negative x cubed. 6x squared minus 10x squared is minus 4x squared. And then we bring down the next term in line, which is positive 2x. Okay, so we want to think to ourselves, what times x squared gives me negative x cubed? And that's negative x. So when I distribute negative x across all three terms, we get negative x cubed plus 2x squared minus 10x. And then I'm going to subtract that result. Okay, so we get negative x cubed minus negative x cubed. That cancels the x cubed terms. Negative 4x squared minus 2x squared gives me negative 6x squared. 2x minus negative 10x becomes positive 12x. And then we bring down the next term in line, which is negative 60. And then what times x squared gives us negative 6x squared, and that is negative 6. So when I distribute negative 6 across all three terms, we get negative 6x squared plus 12x minus 60. And when we subtract that, we get a remainder of 0, just like we are supposed to. Okay, so what we want to do is we want to find the zeros of x squared minus x minus 6. So that very simply, we're looking for two numbers that multiply to give negative 6 and add to give negative 1. And those are negative 3 and 2 respectively. And since the leading coefficient here is 1, then this is going to factor to x minus 3 times x plus 2. Okay, so our zeros. The value of x that makes that first factor 0 is x is equal to 3. The value of x that makes the next factor 0 is x is equal to negative 2. And then we have the two complex zeros. The one that we were given is 1 plus 3i. And then we have its conjugate, which is a 0 as well, 1 minus 3i. Okay, so those are the four zeros of the function that we are given. Again, you will have a test question like this, so make sure you know how to do these for your upcoming test. All right, on to the last set of 3 examples. So these are going to combine like stuff that we've looked at in this section along with what we looked at in the previous section. All right, so the directions here say to find the complex zeros of the polynomial function, and then we're asked to write f in factored form. Okay, and for number 1, we are given the function f of x equal to x to the 4th power minus 1. Now, as I mentioned in the previous lesson on finding real zeros of polynomial functions, if you can factor your function using standard factoring techniques, you want to do that, okay? And we can do that in this particular case. Because when I look at the function f of x here, f of x is the difference of two squares. I can write this as x squared, quantity squared, minus 1 squared. And we know that if we have the difference of two squares, like a squared minus b squared, that's going to factor to a plus b times a minus b. Okay, so that's going to factor to a, which is x squared, plus b, which is plus 1, times a, which is x squared, minus b, which is 1. But we're still not done factoring, because we can factor x squared minus 1 further. That is also the difference of two squares. So I can factor that, x squared minus 1, that's going to factor to x plus 1 times x minus 1. Now, if you were solving this in the previous section where you were asked to find the real zeros, the only real zeros that this has are the values that make those two factors 0, which are x is equal to -1 and x is equal to 1. But it's not asking us to find the real zeros, it's asking us to find the complex zeros. So we actually have to determine the zeros of this as well. So we want to find where x squared plus 1 is equal to 0. And I think the most efficient way for us to solve this is we can subtract 1 on both sides, so we get x squared equal to -1. Take the square root of both sides. So the square root of x squared on the left-hand side gives me the absolute value of x. The square root of -1 on the right-hand side, we define that as I. And then I can drop the absolute value bars, putting a plus or minus in front of the expression on the right-hand side. So this has two real zeros and two imaginary zeros. So the imaginary zeros are x is equal to -I and x is equal to I. Okay, so those are your zeros. It has two real zeros and two imaginary zeros. Now, when it says to write f in factored form, honestly, I don't care if you write the function like this. So in factored form, if you leave it like this, like that's perfectly fine with me. The other option for writing it in factored form is when you have your zeros here, taking x minus each of those zeros to give you your factors. So you could also write f of x as x minus -I, which is x plus I, x minus I, x plus 1, and x minus 1. Like, I would accept that as well. Okay, so either of those two are fine. Like, if you don't want to factor this right here is what's called an irreducible quadratic. Like, you can't factor that in the set of real numbers. If you want to leave that as an irreducible quadratic, that's fine. If you want to factor that irreducible quadratic as x minus a complex number and then x minus the conjugate of that complex number, like we did down here, that's fine as well. Okay, I'll accept either one of those on a test. I'm not sure how the book that I'm assigning homework from, that Algebra 2 book, like how it's going to write the answer. So I chose to write it both ways. Okay, so you can check either way. Okay, so let's take a look at number 2 together, and then I'm going to give you number 3 to work on your own. So for number 2, we are given the function f of x equal to x cubed plus 13x squared plus 57x plus 85. Okay, so again, like the first thing we want to check here is, can we factor this using standard factoring technique? So this polynomial has 4 terms. We want to check and see if we can factor it by grouping. But if we try factoring it by grouping, like my common factor of the first 2 terms is x squared. When I factor that out, that leaves me with x plus 13. Like, there is no common factor for the last 2 terms. So I can't factor that by grouping. Okay, so that's out. So if I can't factor something using standard factoring techniques, we have to use what we learned in the previous lesson. which is using Descartes' rule of signs and the rational zeros theorem to come up with a list of potential rational zeros, and then we have to test to see which one works using synthetic division. Okay, so we want to get the possible number of positive real zeros and negative real zeros. So the positive real zeros are going to be the sign variations of f of x. And when we look at f of x is always positive. So there are no positive real zeros here. That's helpful information, because when we get our list of p over q values, I don't have to test the positive values. The real zeros are going to come from the negative values. Okay, when we take f of negative x, however many sign variations I get there, that's going to tell me how many negative real zeros we potentially have. Okay, so when we take f of negative x, that's going to become negative x cubed plus 13x squared minus 57x plus 85. And when we count sign variations there, we start negative, change to positive, that's 1, change to negative, that's 2, change to positive, that's 3, which means there are 3 or 1 negative real zeros. Okay, then we want to use Descartes' rule of signs. So our p-values are factors of 85, which are plus or minus 1, plus or minus 5, plus or minus 17, and plus or minus 85. Our q-values are factors of the leading coefficient. So the leading coefficient is 1. So the factors of that are just plus or minus 1. So our p over q values are plus or minus 1, 5, 17, and 85. Okay, and of those 8 values, we know our zeros are going to come from the negative values. Okay, so we just have to pick the negative one that works. We just need to get lucky, and I have a good feeling about negative 5. So that one's saying pick me. So I'm going to go ahead and pick that, and I'm going to do synthetic division with that 0. Okay, so we have to check when doing synthetic division, is my polynomial missing any terms? So we go from x cubed to x squared to x to constant. We're not missing any terms, so we just list the coefficients, 1, 13, 57, and 85, and then we just perform synthetic division here. So we're going to put a box underneath that last value to house the remainder, and then we bring down the first number, 1. Negative 5 times 1 is negative 5. That adds up to 8. Negative 5 times 8 is negative 40. That adds up to 17. Negative 5 times 17 is negative 85, which adds to 0. So that's fantastic. That's what we were hoping for. Okay, so that means that negative 5 is a 0, and x minus that number, so x minus negative 5, which is x plus 5, is going to be a factor. And if x plus 5 is a factor, what we find down here are going to be the coefficients of the terms that we get when we factor out x plus 5. Okay, so the resulting polynomial here is going to be x squared plus 8x plus 17. Now, when we look at this polynomial here, like x squared plus 8x plus 17, that's not factorable for us. Okay, so if you can't factor that, then we have to use either completing the square or the quadratic formula to find those zeros. So I'm going to use the quadratic formula. So x is equal to negative b, excuse me, that's negative 8, plus or minus the square root of b squared, so 8 squared is 64, minus 4 times a, which is 1, times c, which is 17, all over 2 times a, which is 1. So we get x equal to negative 8 plus or minus rad 64 minus 4 times 17 is 68 all over 2. which gives us x is equal to negative 8 plus or minus the square root of negative 4 all over 2. So we can rewrite the square root of negative 4 as negative 8 plus or minus 2i divided by 2, which is going to make our complex zeros become negative 4 plus or minus I. And we see that that gives us 2 zeros. Okay, so our complex zeros here are x is equal to negative 4 plus I and x is equal to negative 4 minus I. Those are both conjugate pairs like they are supposed to be. And then the other zero that we found in this problem was over here. That's x is equal to negative 5. Okay, so those are your 3 zeros for that function. Now, when it comes to writing the function in factored form, if you want to leave things in this form, I'm fine with that. If you want to write x minus each of these zeros that we found over here, that's okay as well. Okay, so if you want to write your factored form of that polynomial to be x minus negative 5, which is x plus 5, times x minus negative 4 plus I, times x minus negative 4 minus I, that's perfectly okay also. If you want to distribute the negative, so if you want to distribute this negative here across both of these terms, that, and this negative across both of those terms, that's fine as well. If you do that, you get f of x equal to x plus 5 times x plus 4 minus I times x plus 4 plus I. And that's okay as well. Any one of those three are acceptable. Okay, so with that said, I'm going to have you guys try number 3 on your own. So your function there is f of x is equal to x to the 5th power plus x cubed plus 2x squared minus 12x plus 8. Okay, so let's take a look at 3. Again, this polynomial here has 5 terms, so we can't use like standard factoring techniques with this one. So we have to do just like we did in the previous example, where we used Descartes' rule of signs and the rational zeros theorem. Okay, so to get the number of positive real zeros potentially, we have to count sign variations for f of x. And when we do that, the terms start positive, they change to negative, and change back to positive. So there are 2 sign variations, which means there are 2 or 0 positive real zeros. Okay, to get the number of negative real zeros, we're going to count sign variations of f of negative x. So f of negative x is going to become negative x to the 5th minus x cubed plus 2x squared plus 12x plus 8. So we start negative and change to positive and then stay positive throughout. So there's only 1 sign variation, meaning that there's only 1 negative real zero. Okay, then we want to get a list of our p over q values. So our p values are factors of the constant term. So the factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Our q values are factors of the leading coefficient, which are just plus or minus 1. So our potential rational zeros, our p over q values, are going to be plus or minus 1, 2, 4, and 8. Okay, Now, I know for sure there has to be one negative real zero. So I'm going to test negative values first. I've worked this problem out, so like I don't want to waste time. So the negative 0 that's going to work is negative 2. So we're going to use synthetic division to test there. Now you got to be careful here. When you look at the function f of x, what term is that polynomial missing? And that polynomial is missing the x to the 4th power term. So we have to put 0 as the coefficient placeholder for that term. Okay, so we're going to list the coefficients, which the coefficient of x to the 5th is 1, the coefficient of x to the 4th is 0, coefficient of x cubed is 1, coefficient of x squared is 2, coefficient of x is negative 12, and the constant is 8. All right, so we're going to put a box underneath that last value, and then we're going to test using synthetic division. So we bring down the first term 1, negative 2 times 1 gives us negative 2. That adds to negative 2. Negative 2 times negative 2 becomes 4. 1 plus 4 adds to 5. Negative 2 times 5 is negative 10. That adds up to negative 8. Negative 2 times 8 is 16. That adds to 4. Negative 2 times 4 is negative 8, and that adds up to 0. So that's great. Negative 2 is a 0. X minus that number, so x minus negative 2, which is x plus 2, is going to be a factor. Now, when we factor out x plus 2, this is going to be the coefficients of the resulting polynomial. Okay, so that's going to be 1x to the 4th minus 2x cubed plus 5x squared minus 8x plus 4. And we still can't factor that polynomial. Okay, which means we need to use like synthetic division again. Okay, so we found the one negative real zero that works, which means our next zero has to be a positive real zero. Okay, so we're going to test positive values, and the one that's going to work for us is going to be 1. Okay, so I'm going to perform synthetic division on this polynomial because I want to break down that polynomial even more so. Okay, so I'm not missing any terms there, so I'm going to list the coefficients of those terms. And then I'm going to perform synthetic division. So we bring down the first term 1. 1 times 1 is 1. That adds up to negative 1. 1 times negative 1 is negative 1. That adds up to 4. 1 times 4 is 4. That adds up to negative 4. 1 times negative 4 is negative 4. That adds up to 0. So we already have that x plus 2 is a factor. We know that 1 is a 0. So x minus that number has to be a factor. And the resulting polynomial that we get when we factor that out is x cubed minus x squared plus 4x minus 4. And when we look at this polynomial here, this is actually something that we can factor by grouping. So I'm going to factor this over on the side. Okay, so we have x cubed minus x squared plus 4x minus 4. And I'm going to factor that by grouping. So I can factor an x squared out of the first two terms, which leaves me with x minus 1. I can factor a 4 out of the next two terms, which also leaves me with x minus 1. So x minus 1 is our common factor. And when I factor that out, that leaves me with x squared plus 4. So that's going to make my polynomial f of x be x plus 2 times x minus 1. And then I can write this in this form right here, which means we have another factor of x minus 1. So I can raise the exponent of x minus 1 to the second power. And that leaves me with x squared plus 4 as my last factor. Okay, so when it comes to me finding the zeros, we know our zeros are x is equal to -2. Our next zero is x is equal to 1, and that has a multiplicity of 2 because the exponent for that factor is going to be 2. And then I want to find the complex zeros of this right here. Okay, so I'm going to set x squared plus 4 equal to 0, and then find the complex zeros of that. So that's going to make x squared equal to -4. We can take the square root of both sides, which makes the absolute value of x equal to plus or minus 2i. Or sorry, makes the absolute value of x equal to 2i, and then we can drop the absolute value bars by putting a plus or minus on the right-hand side. So we get x equal to plus or minus 2i. So these are our other zeros. X is equal to -2i, and x is equal to 2i. And again, those zeros are conjugates of one another. Okay, so those are your zeros for this function. If you want to leave the function in this factored form, that's fine. If you want to rewrite it as x plus 2 times x minus 1 squared, and then if you want to rewrite x squared plus 4 as x minus -2i, which is x plus 2i times x minus 2i, that's fine as well. Okay, either one of those is acceptable for the factored form. All right, so that's it. That wraps up this lesson. Again, make sure you guys have this homework assignment done by the time you come to class on Wednesday. Hope you guys have a great day. Take care.